I'm Professor Rad, and this is Precalc video 113, one-to-one functions. In this video, we're going to talk about what it means for a function to be one-to-one, and then we'll do a few examples of checking whether or not a function is one-to-one, both graphically as well as algebraically. So we're going to start out just by remembering something just about functions in general. So remember that if you have a relation, it's going to be a function if every x value in the domain maps to only one y value in the range. So we can test this graphically using something called the vertical line test, right? So the vertical line test says if you have a graph of a relation and you draw a vertical line through it anywhere, if it hits in more than one place, then it is not a function. Right? If you have one single x value, you don't want it mapping to two different y values. You want one input to send you just to one place, to one output. Algebraically, we often see this when there are pluses or minuses involved in our definition for y. So for instance, if I wanted to solve this expression explicitly for y, I could square root both sides. But whenever you take a square root to solve for y, you need to make sure to include the plus or minus, because, for example, if y is 25, its square root could be positive 5 or negative 5. So I can solve here for y and get plus or minus the square root of x minus 5. So when we look at something like this algebraically, we can tell it is not going to be a function, because if I give you one x value, for instance, 6, if I substitute 6 into here, I'm going to get plus the square root of that, and I'm going to get minus the square root of that. So I'm going to get two different outputs from one input. So with a function, if I give you one x, you can only have one possible output, one y value. In order for a function to be one-to-one, the reverse also has to be true. In other words, if I give you an output, a location, a destination that we're going to get sent to, in order to be one-to-one, there's only one possible place it could have come from. So let's write down a definition for what it means for a function to be one-to-one, and then we'll do a graphical example first, since that tends to be a little bit easier to check for. All right, so Lenny here is very excited to share with us the definition of one-to-one functions. So let's check that out. So a function is one-to-one if every y value in the range is mapped to from only one x value. So just like, it's very similar to a function definition, just switching the roles of the x's and the y's basically. So if we can use the vertical line test to check to see whether or not a relation is a function, we can use a horizontal line test to see if it's one-to-one function. He looks so intent, like he's studying it. Okay, so that's what this note here is saying. You can use the horizontal line test to see if a function is one-to-one or not. And incidentally, this one-to-one is a shorthand for writing one-to-one. So 1-1 just means one-to-one. So let's do an example of checking to see whether a function is one-to-one by using the horizontal line test. Alrighty, so for this example, we're going to determine whether or not g of x, which is equal to the absolute value of x minus 2, we're going to determine whether that's one-to-one or not graphically. So to do this, the first thing we're going to do is graph this function. What I like about g of x is that it appears to be a transformation on the absolute value function. So I know my absolute value function is going to look like a v. So we know how to graph that. And then this minus 2 is happening on the inside of the function, on the inside of the absolute value bars. So that means it's going to be a horizontal shift. And it means it's going to go the opposite of the way our intuition tells us. So that means it's going to shift to the right by 2. So if I sketch out coordinate plane here. Ordinarily, my absolute value function has its turning point at the origin, right? So the absolute value function ordinarily looks like this. So we're going to take that and we're going to shift it to the right by 2. So this point is going to go over to 2, 0. And then the point that is normally here at 1, 1 is now going to shift over to be 3, 1. And the one that's usually at negative 1, 1 is now going to be at 1, 1. And that gives me enough to sketch this function. All right. So that's the first part, is creating the graph of the function. Next, we're going to use the horizontal line test. So if I have this function, is there anywhere I can draw a horizontal line and it's going to intersect in more than one spot? Yeah, almost anywhere. So if I draw a horizontal line here at 2, then I'm intersecting this function in 2 spots. So just like with the vertical line test, when you hit in more than one place, it means it's not a function. For the horizontal line test, if it hits in more than one place, it means it's not a one-to-one function. So therefore, g of x is not one-to-one. All right, so now that we know how to do this graphically, let's do a couple of examples of determining this algebraically. All right, started writing some algebra on the board, and Lenny was like, peace out, Ma, I'm leaving. So he was here briefly for us today. But for this part now, we're going to talk about how you can determine whether a function is one-to-one algebraically or not. So I'm going to step out of the way in case you wanted to pause and write down this method here. So our primary method for identifying whether a function is one-to-one algebraically is to say, suppose I have 2 y values that are the same. So that's this f of a and f of b. So I've got 2 y values that are the same. In order to be one-to-one, I have to show that those y values came from the same x value. So that actually, even though the notation makes it look like they're 2 different points, they were the same point because a and b were the same number. So if they have the same y's, then they came from the same x's. If I can't show that, then the function is not one-to-one. So we just saw graphically that this function g of x equaling the absolute value of x minus 2, we saw graphically that that was not one-to-one. It failed the horizontal line test. So let's see algebraically why that's true. So this, much like the even and odd stuff that we did in the previous video, is going to be fairly like mini proof-like. So it's going to feel more like a proof than like a evaluate or solve kind of thing. So we're going to start out with suppose g of a is equal to g of b. So that's going to be your first line for an algebraic solution to showing one-to-one or not. Then we're going to substitute a into the definition of g, and we're going to substitute b into the definition for g. And then essentially what I like to think of it as is solving for a. So I'm going to have the absolute value of a minus 2, because the a is replacing x, is going to equal the absolute value of b minus 2. Now we're going to try and solve for a. So you might be tempted to say, well, if I have 2 things and their absolute values are the same, those numbers have to be the same. And that's not quite true. This is because the absolute value is going to remove the sign of a number. So for example, if I have the absolute value of 3, yeah, that's going to equal the absolute value of 3. But if I have the absolute value of 3, that's also going to equal the absolute value of negative 3. So very similar to when you take a square root, you want to make sure you take the plus or minus the square root, because you could square either the positive or negative version to get that perfect square. If you have an absolute value, you're going to have to pay attention to the same kind of issue. So if I wish to remove the absolute value signs, I can, but it doesn't mean the insides have to be exactly the same. They have to be plus or minus forms of each other. So the way this is going to happen in this equation is I'm going to get a minus 2 is equal to plus or minus quantity b minus 2. And then we can go ahead and solve by adding 2 to both sides. So that will give me that a is 2 plus or minus the quantity b minus 2. Now I can continue to go from here and simplify further, so I will, because I want to make sure I can combine this 2 and this 2 and see if I get 0, because if I'm going to get 0, then I'll get a is equal to b, and we've got a one-to-one function. So to do that, I'm going to split this up into 2 new equations, one where I have the plus and one where I have the minus. So I have a is equal to 2 plus b minus 2, and I have a is equal to 2 minus b minus 2. And then we just simplify those. So on the left-hand side here, because we have a plus, that means I don't need these parentheses, so I can rewrite without them. And then I can combine my like terms. So 2 minus 2 is 0, so we get a equals b. So what this is telling us is one way that I could get the same y values is if I actually had the same x values. So that's what we want for one-to-oneness, but we know it's not one-to-one, so we suspect something fishy might happen over here. So over here, now we have a minus in front of the parentheses, so we have to distribute that to the terms inside. So a is equal to 2 minus b, and then we have a negative, negative makes plus 2. And then I can combine my like terms, 2 and 2 makes 4, and I get a is 4 minus b. So what this is telling us is that if I have 2 points with the same y value, they might have the same x, but they also might not. They might be different by a value of 4. So we found a case where a is not equal to b. So here's an instance where a is not equal to b. Therefore, g of x is not one-to-one. So I'm thinking you can probably see why I said graphically is a little bit easier than algebraically, because we have to go through all of this kind of rigmarole and lots of algebraic techniques to figure out whether or not the function will be one-to-one. So if you have a graph, or if it's a function that's easily graphable, absolutely finding whether it's one-to-one with the graph, really helpful. But if it's a function that we don't know how to graph yet, or maybe it's a function that's got like a constant variable in there. So if I had x minus h, I would need to know how to figure out whether or not it was one-to-one algebraically. So let's do another example of determining one-to-oneness algebraically. Let's try this one out. Alrighty, for this example, we're going to determine algebraically whether or not f of x equals x over x minus 2 is one-to-one. So to figure this out, we're going to start out by assuming f of a equals f of b. So suppose f of a equals f of b, then, and now we're going to substitute in and try and solve. So I'm going to substitute a in wherever I see x's. So I'm going to get a over a minus 2. And here I have f of b. So I'm going to substitute b in for x to get b over b minus 2. Oh, goodness. So this looks like a nice and complicated equation. So let's see if we can solve it. We're trying to get to a equals b. So a good way to do that is to think about solving for a. So one thing that I want to do is get rid of these fractions here. So you can do that either by multiplying both sides by the common denominator, or in this case, because we have a rational expression equal to another rational expression, we can use cross multiplication over the equal sign. So that's what I'm going to do. So I'm going to multiply a times b minus 2. And that's going to equal b times a minus 2. Now, because I have a on both sides of the equal sign, I'm going to want to be able to move around those terms that have an a in them. So I'm going to distribute each expression, and then I'm going to try and get all the a's to the left and all the not a's to the right. So I'm going to distribute the a here. A times b is ab, and a times negative 2 is minus 2a. On the right, b times a is ba. It's a little sheepish there, and then b times negative 2 is negative 2b. All right. Oh, so we have 3 terms that involve an a and just one that doesn't. So let's subtract ba from both sides. So I'm going to get ab minus 2a minus ba is equal to negative 2b. And this is where our friend, the commutative property, is going to help us out. So the commutative property says if you're multiplying, it doesn't matter what order you put things in, you'll get the same thing. So in this case, that means that AB and BA are the same thing. Right? 2 times 3 is the same as 3 times 2. Order doesn't matter. So if I have AB minus AB, they cancel each other out. And so we're going to get negative 2A is equal to negative 2B. And that has made things look a lot nicer for us. So to get A by itself, all we have to do is divide by negative 2. And we end up getting that A is equal to B. So what this is showing is that we have, if we start out with 2 y values that are the same, the only way that can happen is if the x values are also the same. So really, we just have 1 point, not 2. So therefore, f of x is a 1-to-1 function. And there we go. So that's how you can show algebraically whether or not a function is 1-to-1. All right, in our next video, we're going to be talking about 1-to-1 functions, something cool that we can do with them. We're going to be able to find an inverse of a 1-to-1 function. So I'm looking forward to seeing you then. In the meantime, I hope this helped with one-to-oneness, and I hope you have a wonderful day. Bye for now.